Hello, Science 30. This lesson is on alternating current and direct current, or AC and DC. Remember that when we are talking about current, what we're talking about is the movement of electrons that are going through a conductor. So again, think of it kind of like the flow of water going through a river. If we do have a wire, a conductor, we're talking about electrons that are moving through that conductor. So alternating current and direct current are just different ways that the electrons can travel through a conductor like a copper wire. So if we do have alternating current that I have on the left-hand side here, what it says is that the current is moving back and forth. It's going to stop and then it's going to go in the opposite direction. And this is many, many times per second. So if we take a look at the picture here, this is our driving force, our voltage that we have. Conductor that we have going around the outside in a ring, and we have a resistor over here. I, again, is the symbol for current. So what it shows is that, yes, the electrons go in one direction, and then they stop, and they turn around and they go in the opposite direction. And they just keep jiggling back and forth. In the case of direct current, this is now a battery that we have here. Again, we have a resistor and we have our conductor. In this case, the current, if you take a look at the arrow, it's only going in one direction. So in the case of this conductor that we have here, it's traveling around in a counterclockwise direction. So from this battery, it would be coming out of the negative terminal of the battery in this direction and eventually returning to the positive terminal of the battery as well. So I'll just go out of here to show you a really simple little animation. And this animation is one that I just kind of built up from the University of Colorado. And what it allows me to do is conduct two different circuits here. One of them is DC, the one at the top, the one at the bottom is AC. And this just makes it a little bit more visual in terms of the movement of the electrons. So let's start with the one at the top here. This is the DC voltage source, which is a battery. The dark yellowish or orangish bands, that is the conductor. Light in at the top here, and the blue balls that we see, those are representing the electrons. So this would be the negative terminal of the battery. Electrons are coming out, and notice that they're traveling through continuously in one direction, going through the light to provide the energy to turn the light on, and eventually returning to the opposite end, which is the positive terminal on the battery. So that is direct current, where we have the movement of the electrons going in one direction. So if we compare that to the one at the bottom, this is our alternating current voltage source. Now, same sort of setup where we have the conductor in a loop, we have a light. If we take a look at these electrons now, they're moving back and forth. They move in one direction, they stop for a very, very short fraction of a second, and then they travel back in the opposite direction. I have over here at the right-hand side an ammeter, which can allow us to measure the current going through each of these. So if we hook it up to the DC current, first of all, now we can see the graph. And what we have is constant current that's going through this particular conductor. If I switch it around and hook it up to our AC one, that's going to change considerably. Now we're seeing this sine wave. So what this is showing is when it's going up, the electrons are traveling one direction. When it goes back down, the electrons are traveling in the opposite direction. And this just goes on continuously. And hence we get this wave or this sine wave that's being generated from that particular current. So what else about the AC and the DC? Usually when we do think of electricity, we think of outlets in and around our house. You take a device, an electrical device, and you plug it into these receptacles or the electrical outlets. And that is generally what we think of when we do think about electricity. So think about the power lines that are coming into your house. In some cases, they're overhead. In other cases, they're underground power lines. But that electricity that is coming into your house, that is in the form of alternating current. So what are some of the features of alternating current? It is high voltage. So in these power lines here, these might be high voltage power lines where the voltage is into the thousands of watts. Very, very low current, though, very low amperage when we're talking about the alternating current. For the DC, now think about batteries. So whether it is a car battery that we have here, or batteries that you find in smartphones or laptops or flashlights, those are all direct current being generated from batteries. So these ones here, much lower voltage, but they do have a higher current, a higher amp reading. So maybe kind of think about this when you do plug electrical devices into outlets in your house, most of those electrical devices, they run off of 110 volts. There are a couple of them in your house, like an electric range. Those run off 220 volts. And dryers, they run off of 220 volts as well. So these are pretty high voltages. If we compare it to batteries that you might put in a flashlight, for example, that might be 1.5 volts, or they might be a 9-volt battery that you put in. So these ones obviously much, much lower voltages than what we do have that we're plugging into an electrical outlet. So the main reason really why we do use AC for our electricity purposes, for the most part, is we do need to transmit electricity over long distances from where the electrical energy is generated in an electrical generating station, whether it's hydroelectric, whether it's using fossil fuels, whether it's using uranium in a nuclear electrical generating station. From that point, you need to transmit it, typically over long distances, to the people that are using that electricity. So in the case of the AC, what we have is less energy is lost when it's traveling through the wires. Less energy is lost. In other words, it's a more efficient process, and it's more efficient at transmitting that electricity over long distances, which has to be the case when we do have these electrical generating stations that are typically quite a distance away from cities and from industry where that electricity is used. In the case of DC, there is, well, the opposite. So exactly the opposite, what we see on the right-hand side compared to the left-hand side. So on the left-hand side, it was less energy lost. Here it's more energy is going to be lost, and it is simply less efficient to transmit that energy over long distances. So major reasons why we use for most of our electrical appliances, most of our applications are based on alternating current. I have another lesson on generators and motors. So what motors are doing, whether it's AC or DC, motors do the same thing. They convert electrical energy into mechanical energy. And that is the case with both, whether it is AC or DC. So this one that we have on the left here, this is a picture of an AC motor. So electrical energy comes in. What does it do? Well, we have this on the outside here, this rod that's sticking out that's going to spin around, and that is our mechanical energy. Same thing on the right-hand side, only now it's going to be DC current that's coming in. But again, we have this rod here that can spin around, converting the electrical into the mechanical energy. So AC motors, it is kind of important that you know these features of them. So they're usually smaller, which makes them lighter. This rod spins around at a much, much higher rate, so higher revolutions per minute, or RPMs, and these ones are easier to keep cool. In the case of DC motors, well, they're the opposite. They're heavier, they're larger, heavier. They operate under lower revolutions per minute, and they're more difficult to keep cool. The bottom here, I just copied and pasted from a website, so they do identify, yes, well, there are some advantages to AC motors, but there are also some advantages to DC motors as well, and that's why we do also have DC motors in addition to the AC motors. Another major and significant feature in terms of alternating current is for alternating current, the voltage and the current can be transformed. So what that really means is that we can take the voltage and we can take the current and we can either increase them dramatically or we can decrease them dramatically. So this is an electrical transformer here. So the high power lines that we do have, let's say that they are transmitting the electricity at a very high voltage, 20,000 volts. Now remember, when this electricity comes into your house, like I mentioned, it actually comes in on two wires, each one, which carries 110 volts. So what you need to do is be able to change the voltage, take it from a very high voltage and bring it down to a much lower voltage. So this is what we call a step down transformer. And again, I have another lesson, which is dealing strictly with transformers. We can also have the opposite. So from an electrical generating station, it might be generating a voltage at 2000 volts, but we want to transmit it through these power lines at a much higher voltage. So now what we would do is we would do the opposite. We would increase the voltage. So this is electricity that is being transformed, changing the voltage, changing the current. You can do that with AC. You simply can't do that with DC. So I'm going to show you a little bit of an animation here. Again, I do have another lesson which is on transformers. This one here is going to be a nice little bit of an overview. Transformers. I might just have to sleep out of here as well, it looks like. To come up here. Now, I don't think that you can hear the audio on this, so what I'm going to do is I'm just going to turn my speakers off so it's not going to be interrupting us. And then we can take a look at this little bit of an animation here, and I'll kind of walk you through it. It's about 6 minutes long, but I'm not going to play the whole thing for you. Showing us here, first of all, this wave that we do see. And we already saw this wave, this sine wave, which is an indication of the alternating current. So here we're circling around this transformer here. This is what is referred to as a three-phase transformer. And what it involves is a series of different coils that are referred to as solenoids. So as we get to the inside of this transformer here, we'll see these three different solenoids. Again, in another lesson, I do talk about this electromagnetic induction. Whenever you do have a current that is going through a conductor, and we do have a ring-shaped conductor here, whenever you have a current that is going through, electrons that are going through that conductor, it is automatically going to generate a magnetic field. So what it's showing here is that the magnetic field is going in one direction, and then it changes and it's going in the opposite direction. And that's because the current is alternating current. Now we're taking a look at, well, two different conductors, this straight one here. Now we have the current going through from the top to the bottom, and we have that magnetic field that circles around that conductor. I'm just going to stop and go back there a little bit so we can see that at least again. So this is our single wire conductor. The electrons are going from the top to the bottom. And we use the right-hand rule in this case to determine the direction of the magnetic field. And here it's looping around this straight wire conductor, going in a clockwise fashion. In the case of transformers, instead of a straight wire, we have a coil of wire or a solenoid. So they're going to show us again here that this one is going to be alternating current in the solenoid as well. And because it is alternating current, and we can see that flipping back and forth with the arrows here, showing the electrons going in one direction and then the opposite direction. On the inside and looping around the outside of this solenoid, it's showing the magnetic field that's being generated. And what it was showing again is that it's flipping around and it's going in opposite directions. This is the general setup of a transformer where we have two different coils, two different solenoids. So we have electricity coming in on the left-hand side. That's what we call the primary coil. And the one on the right-hand side where the electricity is going to be coming out, that is the secondary coil. So it's going to come in on the left-hand side with a certain voltage and a certain current. And it's going to come out on the right-hand side with a different current and a different voltage. These two conductors, these two solenoids, these two coils, they're not physically connected to each other. So down at the bottom here, they're identifying something that's called the magnetic flux. As soon as you have current that's going through this solenoid on the left, it generates a magnetic field. This magnetic flux that can travel through this soft iron core, and it can transmit that magnetic field effect to the second solenoid. And what that can do is induce or generate electrons moving through the secondary solenoid. I'll stop it again for a second here, just to sort of explain the differences that they were trying to show on the right-hand side. So once again, once we have electrons that are traveling through this solenoid, it sets up a magnetic field, and that magnetic field, or magnetic flux as they identified, is passing through this laminated or soft iron core. No connection between the electrons going through the solenoid on the left and the one on the right. It is the movement of the electrons that induces or creates the magnetic field. And it's the magnetic field that's now going to induce or create the movement of electrons in the secondary solenoid. So whether it is a step up or step down transformer will be determined by the number of turns in the coil on the primary versus the secondary side. If you have fewer turns on the secondary side, then it's going to bring the voltage down. If you have more turns on the secondary side, that's going to bring the voltage up. So the first one is what we call a step down transformer. This one here would be a step up transformer. So that's all I'll play of this one. That's the basic sort of design and layout of a transformer. And again, I do have another lesson that is dealing with transformers, actually transformers, generators, and motors, where I go into more detail and I go into some calculations for transformers as well. So finally, what I have here is just the voltage graphs, and this could be voltage or current actually, for direct current and for alternating current. So the key is that the voltage is going to be constant. The current is going to be constant if it is direct current. For alternating current, this is what you're looking for. You're looking for this sine wave. So again, as it goes up, the current is going in one direction. As it's going down, the current is going to be going in the opposite direction.